This video, the second part for Lab 8, we're going to develop the tools for constructing confidence intervals. And so to do this, we will draw pretty heavily on the central limit theorem described in the last chapter, or last section. And so to review, the central limit theorem in a nutshell says if you collect a large enough sample and want to calculate the proportions of all the different samples you collect will follow a normal distribution where the mean is the population mean and the standard deviation of these proportions that we're collecting follow this formula. So this is what we're getting into. So to put this into context, these tools are used to address some pretty pertinent questions. So the first example we're going to look at is a voting poll. Suppose, actually this is a poll that was done pretty recently. We have a poll of 809 voters, 44% of which indicated they would vote for Donald Trump in the next election, and 50 indicated they would vote for Joe Biden. So this provides some evidence of how people will vote in the upcoming election. But no, it's not the whole voting population. 809 is still a relatively small sample. So we have this question, to what degree can we use this poll to describe overall voter ratings? So for this, we will use the central limit theorem. If it applies, we'll have to check some of the conditions that apply. The point estimate for the sample proportions, both for 44% and 50%, will follow closely a normal distribution. So we can use the standard deviation and mean to calculate confidence intervals, as we'll describe. So the hardest thing we'll have to calculate is the standard deviation of the sample proportion, which is called the standard error, using this formula. And if we can do this, we can calculate the confidence interval, P is the proportion, plus or minus some z-score times the standard error. Remember, standard error is one standard deviation. So if we want to know how much percent of the potential range of voter ratings cover, we can adjust this value of z. So here we'll see an example. What if we want to cover 90% of the possible data? If we want to have 90% of all this normal distribution, we can use this function qnorm, which finds the quantile. So I'm going to write this out. We want to cover 95% of the data, but that'll be centered around the mean. So really, we want to go from from 2.5 to 97.5 of all the data. So I'm going to describe why this is. Why don't we go from 5% to 95%? This is kind of a nuanced issue that can be overlooked. If we look at this range here, we're actually only covering 90% of the data, right? If we look at this one, 95 minus 2.5, we get 95% of the data. So do you see we have to split the difference, and for wanting to cover all but 5% of the data, we divide that 5 into 2 and add it to, we got 2.5 to 100 minus 2.5 is how we do that. So if we want to cover all but a percent of data, this is just a general formula. If you need it, we go from a over 2% to 100 minus a over 2%. And that's how we got this is the value we want. Okay, so to do that, we have the maximum quantile of 95 plus, well, I'll do it this way, 100 minus 0.05 divided by 2. Oh, but I have to say 1 because I'm not looking at percentages anymore. This has to be a decimal value. Notice it returned something that said NaN, which is not a number. So what that means, So let's try it again. Okay, so what this says, if I want to cover the upper limit of my 95% of data, I have to use this value for z to be 1.96 about. So 1.96 is the upper value for z. And if I want to find the minimum, I would say 0.025, which is 5% divided by 2. And notice that gives me negative 1.96. So this ensures if I look at everything between negative 1.96 standard deviations and 1.96 standard deviations, I cover exactly 95% of the data. So a way to write that concisely is p plus or minus 1.96 times the standard error, which is the standard deviation of the sample. Another way to express that is using interval notation, this being our minimum value, and this is our maximum value. Okay, so this is kind of theoretical, but let's just like generalize it. We could say, what if we only want to cover 90% of the data? We would say the same thing as above, but if we cover 90% of the data, there's 10% that we're not covering. So we say 1 minus 10% and over 2 and 10% over 2. So notice this goes between 5% and 95%. So we've covered 90% of the range. So those are our values. So our confidence interval will be p, well, I'll do it this way, p minus 1.64 times SE up to p plus 1.64. So that's my confidence interval. And if you want to write it using an equation, just put dollar signs around it. So it makes it look pretty. How do we do 1% of the data? If we wanted to cover all but 1% of the data, 99 has only 1% outside of the interval, so we're going to go like that. And so you see that this covers 99.5% and this is 0.5%. So that covers 99% of the data. And if we want to find out what range of our actual data, it'll be from p minus 2.5758 really, standard times the standard error, and p plus 2.58 times standard error. Let's put that in an equation so it looks nice. Okay, so what these formulas are showing us is if we want to construct a range of values with which our data is likely to fall in, we take the fact that this distribution is going to be approximately normal and use the properties of the normal distribution to find out what range our data should fall in. Okay, so this is some application of what we've done before. To this question, what is the actual confidence interval for a proportion of people who voted for Trump? What does this data tell us? What range of values are likely? So to answer this, we first have to check, does this study, the conditions of this study, satisfy what the central limit theorem says is needed for the central limit theorem to apply? So remember, the conditions are n times p has to be greater than 10, and n times 1 minus p has to be greater than 10. So what is n in this study? N, I believe, was 108, 109, 809. 809 people were surveyed for this. And the sample proportion was 0.44. So if we run that, notice all these values, n times p and n times 1 minus p are greater than 10. That's just a check we have to do to make sure we're not dealing with too small of a sample size. So we're good. Assuming the voters that were selected randomly, so we can assume they're independent. Okay, so given this, given n and p, what is the sample proportion? Well, the sample proportion was just 0.44. And the standard error is a little more complicated. Let's call it standard error. It's the square root of, I even have to look at it, p times 1 minus p over n. So p times 1 minus p over n. So let's look at what the standard error is. So it's the standard error in terms of percent is 1.75% about. So this is the standard deviation of our sample. It says that if we want to find, remember from that 68, 95, 99 theorem, says about 68% of the data will fall between 1.75 and above and below 0.44. So to construct the 95% confidence interval, to be more precise, 95% confidence interval said we're looking at p minus 1.96 times the standard error and p plus 1.96 times the standard error. So this tells us the minimum value that's in our 95% confidence interval and our maximum value. So to interpret this, we should say the 95% confidence interval, CI for short, is from 40.58% or 40.6% to 47.4%. So this means if we were to sample again and again, lots of times, and construct confidence intervals, 95% of them would fall between this range. Okay, 95% confidence interval. Now let's do the same for Trump. Oh, this is say Biden here. Okay, Trump had 44%, Biden had 50%. So we can construct the same confidence interval for Biden and see, okay, do they overlap? And if they do, then that means we're not certain who's going to win. This study doesn't determine conclusive evidence. It doesn't provide conclusive evidence. So, same drill. Do the conditions for the central limit theorem apply in this case? N is the same number. P is now 50%. So I have to look at n times p and n times 1 minus p. And just check, do these fall above 10? And if so, we can apply the central limit theorem. So now we have to find the sample proportion is just 0.5, and the standard error is the square root of p times 1 minus p over n. And this tells us what the standard deviation of the sample is. So to construct the 95% confidence interval, we're going to do 1 minus 1.96 times standard error plus 1.96 times standard error. And this tells us the range that is likely for 95%. Given our sample distribution, 95% of our samples will fall in this range. So the 95% confidence interval for Biden's ratings, or people voting for Biden, are 46% to 53.4%. So now the real question, do these values, given those values and these values, do we have conclusive evidence as to who's going to win? And notice, since these overlap, that interval overlaps with this interval. This study, with 95% confidence, using this tool, we don't have evidence Biden will win because the confidence intervals overlap. Okay, so that's one of the first tools we're going to use for testing hypothesis, is constructing these kind of intervals and comparing them and seeing how what kind of certainty they give to the questions we're answering. So there's one more poll that's with a larger sample size, so that gives us a slightly greater advantage in some of the conclusions we can draw from it. So you'll do the same process with this poll. So construct your intervals, the proportion of people favoring each candidate, and then use that to summarize what this data suggests about the outcome of the election. All right. Good luck.